All right, 5.1, estimating with finite sums. So example 1. A train moves along a track at a steady constant rate of 75 miles per hour from 7 to 9 a.m. What is the total distance traveled by train? So if you do recall, the formula for distance is distance equals rate times time. My rate is the 75 miles. The time is how many hours from 7 to 9. So it's 2 hours. Okay, so distance equals 75 times 2, right? Easy peasy, lemon squeezy. 150, okay, so 150 miles is how much was traveled. All right, B. Using the graph of the situation above, we can indicate the total distance traveled geometrically. In calculus, we use integrals to do the same thing I just did in example A, or part A, with more complicated graphs, of course. But I'm just starting off with a simple graph. Using this graph, I can actually get the same answer, but using geometry. So let me label the graph. So here's my graph, right? The velocity is the miles per hour, so I went by 25, 50, 75. The time is the hours, so from 7 to 9. All right, now the idea is that I can get the same amount, or the same answer, by using area. I'm going to look at this graph, and I'm like, okay, I want to know how much distance was traveled from 7 to 9. So 9 is going to be my cutoff point here. Pretend that's a straight line. And I can figure out the amount of distance traveled by simply finding the area underneath this graph. If I find the area underneath this graph, then I will find the amount of miles traveled, the distance. So this is an easy geometric figure. It looks like a square, but it's probably more like a rectangle. And if you recall, area of a rectangle is just length times width. If I find the area of this rectangle, I will be able to tell you the distance traveled. Okay, so area is length times width. So let's call this length 2, because it's 2 hours from 7 to 8 and 8 to 9. And let's call the length here from 0 to 75. It is 75. Okay, so from 7 to 9, let's call that the width. It'll be 2. And from 0 to 75, let's call that the length. It'll be 75. So 75 times 2, and voila, I get an area of 150. But what it actually is the distance traveled. The distance traveled, which was 150 miles. This is how integrals work geometrically. And we're going to start off with the geometry, and then we'll do the algebraic stuff. Part C. Suppose the velocity function in miles per hour was given by v of t equals 6t minus t squared. Do you think we could use the same method as above to find the distance traveled? Okay, so in the other example, it was a nice straight line, so we could make a rectangle. Here, my graph is a parabola. It is very much curved. But yes, we can use the same method. If I find the area geometrically underneath that curve, I can tell you the distance traveled. Now, for a curve, because they're not just perfect little quadrilaterals, a chart is pretty much a necessity. So I get some values for t, and I'll plug them into my velocity function. And I'm going to go ahead and label the graph. Okay, so there's a way for me to find the distance traveled by using area, but this is a curve. So use something that you're good at finding the area of, like a rectangle. For example, let's say here at 4 and then at 2. I can find the area of that rectangle. It's 8. 2 times 4. And then let's go all the way up. We'll see if I can make a straight line. Up here and then up here. See, this one wasn't even that straight. Up to let's use 9. So it's a little over, right? So that's a 2 by 9. So it's 18. And then on the other end, I'm just going to do the exact same thing. A 2 by 4. So notice, okay, it's a little bit extra, right? I have, oh, let me write down that that's an 8. I have a little bit of extra space here, and a little bit there, right? Okay, but let's see. The area is 8 plus 18 plus 8. Well, that's 16 plus 18, so that's 34. My area is 34. Okay, now I'm going to tell you that the area underneath that curve is 36. Later, you'll figure out how to do that on your own. So that's pretty close. 34 is pretty close to 36. I mean, I do have all this extra space, right? Because this is what I really needed, but then I have all this extra space here. But then I'm like under here. I didn't count that, and I didn't count that, right? All right, so that's one way. Now, if I wanted to be more accurate, what would make sense? Currently, I'm using 3 rectangles. But if I did want my answer to be a little more accurate, what would make sense? Hopefully you're thinking, okay, Mrs. Rondon, instead of 3 rectangles, could we use more rectangles? Instead of fat rectangles, 3 fat ones, let's use skinnier ones. Maybe 6 skinnier ones. That's what I'm going to do. Now, you could use the table, right, that I have drawn here. And the table is, my t values are from 0 to 6, and then I plug them in, and I get my v of t values, basically my y's. What the velocity is when I plug in 0, 1, 2, 3, 4, 5, 6. Now, you can use that, or you can just eyeball it. But if you want it to be more accurate, using your table could be helpful. So let's see. For the first rectangle, I'm going to make it 1 unit wide instead of 2. So I can have 6 different rectangles. And I've decided that it's going to go up to 4 right here. I mean, I could use 5 if I want. But I'm going to go can't talk. I'm going to go ahead and use 4. And if you know anything about symmetry, then I'm probably going to use the same number right over here. Just pretend that I actually drew that to where I needed it to be. Oh boy. All right, so 4 more to go. For the next one, again, I could use my chart. I could go all the way to 8. But I'm not, what's the word? I'm not stuck going all the way to 8. So let me go to 6. I'm just showing you 2 different ways, right? I could do whatever numbers I really want, or I could use the numbers on my chart here. The idea is just to get closer. I don't have to be exact. For the next one, I don't know, I feel like going up to 8. Like, okay, for the next one, maybe I feel like going all the way to 9. I didn't have to. And for the following one, what do I feel like doing? Let's throw in a 7. Why not? All right. So the idea is that this one, because I have more rectangles and I do fill up more of the space. Like I only have this little bit left over and this little bit left over and this left over and this, right? As compared to before. But I do have all of this right here that I probably, well, not probably, I don't actually need, and this right here that I don't actually need. Okay, there's a dozen ways to write, to draw the rectangles, right? I'm just trying to get my point across. But let me see what my area is. Okay, so for the first one, that is a 1 by 4. Second one, that's a 1 by 6. And the third one, that's a 1 by 8. But then the next one, I decided to go up to 9. But then that one, I decided to use 7. And then for the last one, I kept it symmetrical, and that's a 1 by 4. So let's see, 4 plus 6, 10, plus 8, 18, plus 9, 27, plus 7, 34, plus 4 is 38. Well, look at that. It's an overage. It's just as far from 36 as 34 was. But I guess it's higher rather than lower, right? I can draw the triangles, or the rectangles, my bad, using these numbers instead. And I don't even need to graph them. I could be like, okay, the first one is going to be a 1 by 5, right? Because of the 5 here. I'm not using the graph, so 5. The second one is going to be 8 tall, so 1 by 8. The third one's going to be 9 tall. The fourth one's going to be 8 tall. The fifth one's going to be 5 tall. And the last one's going to be 0 tall. You're like, what? Yes, that's okay. So let's see, what do I get here? 5 plus 8, 13, plus 9, 22, plus 8, 30, plus 5, 35. Oh, look at that. That's even closer to 36. Okay? Basically, this is what we're doing today. All right, example 2. Use 5 rectangles to find 2 approximations of the area of the region lying between the graph of f of x equals negative x squared plus 5 and the x-axis between x equals 0 and x equals 2. So I want to approximate the area underneath this graph. I don't have the graph. No biggie. 0, 1, 2. So my graph, you know what, let me make this fatter. Let me make it fatter. There we go. I'm going to need a table. So make a table real quick. X and f of x, right? Which values am I going to plug in? Oh, they want me to make 5 rectangles. How can I divide from 0 to 2 into 5? Right? Yes. 2 divided by 5. So let's see. 2 divided by 5 is 0.4. OMG. The way that we normally make a graph, like 1, 2, 3, 4, 5, not going to be so helpful here. But since they want me to make 5 rectangles, I'm going to go ahead and do 2 divided by 5, right? Because it's from x equals 0 to x equals 2, which are 2 units. Divide that up into 5 pieces, and I get 0.4. So let's see. 5 pieces. This will be 0.4, this will be 0.8, this will be 1.2, this will be 1.6, and that'll be 2. Now, those are my x values. So 0.4, 0.8, 1.2, 1.6, and 2. Plug them into the equation, and we get, oh, I'm forgetting a number. Okay, let me backtrack that real quick. Let me just move this slightly up. Leave that space there, folks. Sorry. Right, so plug those suckers in, and I get 4.84, 4.36, 3.56, 2.44, and 1. Now, as you can see, it said to find 2 approximations. In this example, we're using rectangle approximation methods to find area. Now, a rectangle approximation method, and no, goodness gracious, we're not going to have to say that. We're going to abbreviate it to RAM. There's 3 kinds. There is the left RAM, which is called LRAM, the right RAM, which is RRAM, and the midpoint, which is called MRAM. These are 3 different approximations that are used in calculus to find area with rectangles. Now, LRAM, the left part means that you're going to use the leftmost part to as the height of the rectangle. RRAM, you're going to use the rightmost point, and midpoint, you're going to find the midpoint, and you're going to use that to find the height of the rectangles. So that's why I needed the space inside of my little table here. So since I'm using LRAM, and these are my 5 intervals, I'm going to have to use the leftmost point. So for the first rectangle, the leftmost point is 0. So I'm going to need 0. And when I plug in 0, I get 5. All right, so I'm going to graph the equation. So 0, 5. Oh, it might help if I actually have my... So 0, 5, right there. 0.4 is 4.84. Ew. I don't want to figure out where 4.84 is. Just do a nice little guesstimate. Let's say right there. Let's skip to 1.6. 1.6 is 2. You know what? Let's do 1.2. 1.2 is 3.56. So it's about right there. And then 2 is 1. So 2 is going to end up about here. So my graph should look something like this. Okay, let's pretend I hit the dots. It is an upside down parabola, so it makes sense. And I'm finding the area underneath that. So my first rectangle, because I need 5 of them, has to start from here, my leftmost point. So I move to the right, and then I come down. That's going to be my first rectangle. Now the area of this rectangle is 0.4 times 5. Okay? My second rectangle is going to start at the leftmost point on the graph, which is right here. That is the leftmost point on the graph for the next rectangle. And then to the right, and then down. My next one is going to start on the leftmost point of the graph for this rectangle, which will be the 0.8 at what, 4.36, and then to the right, and then down. Okay, the next one, I'm going to do it in black. It's going to start here, which is the left point, and go over to the right, and then come down. Gosh darn it. And then, let's pretend that works. Okay, last rectangle. I'll make it in yellow. Starts here, and then moves over, and then down. Okay, so I'm going to use these 5 rectangles to approximate the area. This is LRAM. So LRAM, oh, this is still in yellow. I don't want yellow. Yellow. LRAM is going to be the area of each rectangle. So the first one is 0.4 wide times 5. That's the height. The second one is still 0.4 wide, but times a height of 4.84. The second rectangle, this one right here, oh wait, the third rectangle, sorry, this one right here, is going to be 0.4 wide, but with the height of this point. And what is the height of that point? 4.36. The next rectangle, which is this one right here, is 0.4 wide, but it has a height of the left point, which is right there, 3.56. The next rectangle, which is this one right here, has a width of 0.4, but the height is the 2.44. Okay, I hope you see the pattern here. For this one, the height is this left point. For the first rectangle, the height is that left point, it's the 5. Okay. All right. So that's what LRAM is. Use the height on the left, the highest point on the left for that specific rectangle. Now, if you notice, all of the widths are exactly the same. They're 0.4. So we could make our lives easier just by going ahead and deciding, all right, it's 0.4 times all of the heights added up. Okay, because what I'm doing is 0.4 times 5 plus 0.4 times 4.84 plus 0.4 times 4.36, etc., etc., etc. Well, instead of doing all of that one by one, we could just do the 0.4 on the front and then add up all of the heights. So it'll be 5 plus 484 plus 4.36 plus 3.56 plus 2.44. Now the 2.44, this right here, is the leftmost point for this little rectangle here. Okay? Notice, I do not use the 2 and the 1. Did not use that because the 2 would be here. 2, 1 is right there. Okay, a little lower. It is not the left point. It's actually on the right side of that rectangle. So I wouldn't use that for LRAM. All right, so add the 5, 4.84, the 4.36, the 3.56, the 2.44, and we get, oh man, I didn't do it. Well, hold on. All right, so we get 20.2, and then actually multiply that with the 0.4, and it is 8.08. And that is the area underneath that curve. All right, so again, there's 3 kinds, LRAM, RM, and MRAM. Right now we're only doing 2 approximations, so A, we did LRAM. For B, we're going to do RM. Same idea. I need the same exact, what do you call this? Oh my god. Table, or chart, or T-chart, or whatever you want to call it. So here, example 2B, I'm going to do the exact same thing. All right, so for this one, RM, I'm going to have to use the right point, the point on the right. And I don't mean the correct point, I mean the point that is on the right. So 5 rectangles again. So here we'll go, that's my first rectangle, and I'm going to use this height. Okay, that is the height on the right. And then this will be my rectangle. Okay, for the next one, I would use the height on the right, and then this. On the next one, I'll use the height on the right, and then this is my rectangle. On the following one, I'm going to use the height on the right. And then last but not least, I'm going to use the height on the right. Okay, now I do need to know what these heights are. So I plug in 0.4. And we already know what we have, or what we get, because we would have done this already for part A. So 4.84. And then I plug in 0.8. And we get 4.36. I mean, this is familiar, right? From the same thing. Same thing. Okay, so I want you to see, right? I'm using this time the right, the point on the right. That's what LRAM means. Okay, that's going to be my height. My widths are all the same. Again, the width is 0.4. So 0.4 times all of my heights. Okay, so 4.84 plus 4.36 plus 3.56 plus 2.44 plus 1. Now notice, this time around, I did not use 0, 5. I didn't use this point. That's kind of big. I didn't use this point right here. Right? That's why I didn't include it in my T-chart or my table. So for LRAM, I didn't use the last point because it was on the right. And for RRAM, I didn't use this because it was on the left. Okay? All right, so pop that in the calculator. 0.4 times all of that is 6.48. Now notice, this is the same equation, same graph, but my area is a lot smaller than it was for the LRAM. And the reason for that is, if you pay attention, in this graph, I have a lot of space left over. Because this graph is concave down and decreasing, for RRAM, I have a lot of space left over. So this is actually an underestimate. Okay? This is an underestimate. Now if you go back to the LRAM graph, if you look, all of this is extra because this graph is concave down and decreasing. And so therefore LRAM is an overestimate. The way the graph is going, and which method you use does determine if it's actually an overestimate, if it's an underestimate. So that's something to keep in mind. All right. Go ahead and try it. I'm going to do this in class. Example 3 is the same stuff from the try it, but it's MRAM. This time we're doing MRAM. And MRAM is a lot more complicated because it uses the midpoint. So for example, this graph, they want to know the area from 1 to 3, and they want us to use 4 rectangles. So I'm only going to focus from 1 to 3. This is the area I'm going to focus on. Oy. If only this was as easy as it is on paper. So this is the area I'm going to find. This right here. Okay, I'm not going to find anything else. And they want me to split this up into 4 rectangles. Okay, so we have to start using 1.5 and 2 and 2.5. But not only that, when we use MRAM, we have to use the midpoint of the rectangle. For LRAM, we use the height on the left. For RRAM, we use the height on the right. Well, for MRAM, I have to use a height that's exactly down the middle of the rectangle. So my table is going to be slightly different. They want 4 rectangles. I'm going to have to make them, like for example, the first one is going to have to go somewhere here, right? That's my first rectangle. Well, the height I need is the middle, the midpoint between 1 and 1.5. And in order to find that midpoint, I'm going to have to use x is, now what's in between 1 and 1.5? 1.25. And then that's what I'm going to plug in into my equation. And what I get is 1.0625. Okay, for the next rectangle, I'm going to make the rectangle here. And I need the midpoint of this rectangle. I need the middle. Where does it hit the graph? So between 1.5 and 2 is 1.75. And when I plug that in, I get 1.5625. So hopefully you're getting the gist of it. Let's see. For the next one, it's going to go about right there. Oof, that line is not straight. We're going to work with it. Not even. Too far, Narita. Too far. Alright, let's do this again. Uh-huh. And uh-huh. But I need the middle. See, the middle hits right here. So, da-da-da-da. There you go. Uh-huh, uh-huh, uh-huh. So like I said, the middle hits right here. So if you notice midpoint, I have a little bit of an overage here, but I'm going to be a little bit under right here. Okay? So midpoint is going to be a little more accurate. So I plug that in. The last one, I'm going to need the midpoint in between 2.5 and 3. And it meets right here. So, uh-huh. And uh-huh, 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 uh-huh. And there you go. I'll finish filling out the table. All right, so MRAM requires the midpoints, not the left or the right point. So you're most likely going to have to figure out what the midpoints are and then plug them into the equation and get your heights. Again, the width here, what is the width? Well, it's going by 0.5, 0.5, 0.5, 0.5. So the width is 0.5. And then all I have to do is add up the other heights. 1.0625 plus 1.5625, etc. All right, so you add them all up, and then we get our answer. 0.5 times 9.25. And then if you actually multiply that, it's 4.625. Now notice, 4.625. If you did your try it, the LRAM was 3.75. The RRAM was 5.75. But MRAM is actually in between those two. Okay? If you did the try it, you see that the LRAM was an underestimate because from 1 to 3, this graph is concave up and increasing. MRAM this time was an overestimate because it is concave up and increasing. So MRAM actually lies right in the middle. Okay? All right. Last, certainly not least, or second to last, I realized that I called this example 4 and what is it? This one. I call this one example 4 on your notes, and it should be 3, and the next one is 3 instead of 4. I was going to switch their places, but then I decided to leave them how they were. Sorry. Okay, the table below shows the velocity of a model train engine moving along a track for 10 seconds. Using a rectangular approximation method with 10 sub-intervals, estimate the distance traveled by the engine in the first 10 seconds. This is a chart. There is no graph. We are not going to graph this. We're going to answer this using the chart. They want us to use 10 sub-intervals. That's basically saying 10 rectangles. All right, so A is LRAM. Remember, LRAM, we have to use the leftmost point. So the leftmost point, or the height on the left, is going to be this 6 right here. Now, the width. I'm using 10 sub-intervals, and if I look at the time here, I go from 0 to 10. So the width is 1. Okay? So my width is 1. And then I would just add the heights of all 10 rectangles. And I would start with the very first one because that is the height on the left. I'm just going to make a rough sketch here. So let's pretend this is 6. And then this is 1. Maybe I shouldn't have made that one 6. Let's pretend this is 6, this is 12, and this is 22. Okay, I'm just making a rough sketch. Do not draw this. I want to show you what I'm talking about. So 0, 6, that would be the first one. 1, 12, that would be here. 2, 22, that would be there. Oh, and then 3, 10, about there, right? Okay, so whatever this curve looks like, oof, that's horrible. I would be using the left point for each one, right? Oof, that's horrible. So I'm going to use the very first y value or velocity. Okay. All right, let's get rid of that. So it's going to be 6 plus 12 plus 22 plus 10 plus 5 plus 13 plus 11 plus 6 plus 2 plus 6. What did I not include? I did not include the last one because that's going to be on the right. I already have my 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the heights for my 10 rectangles. Okay? All right, so add all those babies up, and I get 93. And that is the distance traveled by the model train in 10 seconds. For all I know, it's probably, oh, it's inches. Haha, it's right here. Inches. 93 inches. All right, RAM. Same idea. But this time, since I'm going to use the point on the right, I am not going to use the first one, but I will use the last one. So the width is still 1. I don't really need that, right? Hopefully you see that. And then this is the height of my first rectangle. And of course, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I do have 10 heights. So what is the last one? 0. I have 10 heights. So add those babies up. 12 plus 22 plus 10 plus 5 plus 13 plus 11 plus 6 plus 2 plus 6 plus 0. And I get 87. So as you can see, LRAM in this case is most likely the overestimate and RM is the underestimate. Right. Here's your homework. See you in class. I will do the try-its in class, even though I gave you the answers.